Module 2, Lecture A, Slicing and Views. By the end of this lecture, you will be able to use basic slicing and step slicing to select subarrays from one-dimensional and multi-dimensional ndarrays. Distinguish between views and copies in NumPy 2.2.6 and predict when slicing operations share memory. And reshape and flatten arrays while reasoning about when the resulting arrays are views of the original data. Basic array slicing. Slice, start, stop step. When working with arrays, you often want to focus on a specific segment rather than the whole thing, such as a week of temperature data. Slicing lets you do this by choosing a start position, a stop position, and an optional step size along the array, which is indexed starting at 0. The stop position is not included in the slice, a convention called a half-open interval, and this makes it easier to predict slice lengths and combine slices without off-by-one errors. Overall, slicing is an efficient way to select parts of an array without manually looping through each element. Think of a long array of hourly energy use over many days. To select the first 24 hours, you start at position 0 and stop just before position 24. If you leave out the starting position, it automatically begins at the start of the array. And if you leave out the stopping position, it continues to the end. A step value controls how densely you sample the data. A step of 1 takes every hour. A step of 2 takes every other hour, and larger steps take every few hours. This idea is useful when you want to reduce data, such as keeping every 5th sensor reading or every second video frame, for a more compact summary or analysis. Using negative values and defaults in slicing makes working with sequences more flexible. Leaving out the start and stop while using a negative step quickly reverses an array, which is useful for accessing recent items such as logs or scores. Negative indices let you count backward from the end, so you can easily select elements near the end without including the final position. Overall, this approach lets you efficiently choose ranges, skip through data, and reverse order without writing manual loops. Python code. Slice, start, stop, step. This section demonstrates basic NumPy slicing on a one-dimensional array using start, stop, and step values. It explains how slices select specific positions in the array, beginning at a chosen index and ending before another. You also see how to skip elements by using a step greater than 1, which picks every second or third value, and how to reverse the array by using a negative step. Clear printed results show how each type of slice changes which elements are included. In this script, we first import NumPy, a key Python library for efficient numerical computing. NumPy is especially useful for creating and working with arrays. Here, it is used to build and manipulate a one-dimensional array that stores hourly temperatures. Importing NumPy gives us the array tools we need to perform slicing and other operations on this temperature data. We begin by creating a one-dimensional array with NumPy that stores hourly temperatures in Fahrenheit. This array, called hours, holds a sequence of temperature values. Its main purpose is to serve as a simple dataset that we can later manipulate with slicing. Using this array, we will explore different ways to access and select specific parts of the data. We begin by printing the original array of hourly temperatures, so we have a clear reference for the data we are working with. Seeing the full array first makes it easier to follow how each slicing operation selects certain elements from it. This visual comparison helps you understand how different slices relate back to the original set of temperatures and what portion of the data each slice represents. We take a slice of the array starting at the beginning and ending just before the fourth position, which gives us the first 4 elements. This slice uses the default behavior of moving one step at a time, so it includes every element in that range. We then display these 4 values to show the result of the slicing operation. In this example, we create a slice of the hours array by leaving out the starting index, which makes it default to 0, and setting the stopping index to 8. This selects elements from the beginning up to, but not including, the position at index 8. We also set the step to 2, so the slice takes every second element within that range. As a result, we get every other hour from the start of the array up to index 7, and then we print these selected values. We create a slice of the hours array starting at index 3, which is the 4th element, and we do not give an endpoint, so the slice runs to the end of the array. We use a step size of 3, so we take every 3rd element starting from that 4th position. This means 2 elements are skipped between each selected value. Finally, we print this slice to show which elements were chosen by the slicing operation. To reverse an entire array, you can use slicing with a negative step, which flips the order of the elements. This tells the program to start from the last element and move backward to the first. By leaving out both the starting and ending positions, the slice automatically includes the whole array. When you print the result, you see the array elements listed in the opposite order from the original. We create a slice of the hours array using negative indices to select elements starting from the 5th position from the end up to, but not including, the last element. This produces a middle section near the end of the array, which is stored in a new variable. We then print this new variable to show the selected values. This demonstrates how negative indices let you access elements relative to the end of an array. This script uses a one-dimensional NumPy array of hourly temperatures to demonstrate basic slicing techniques. It first shows the full array, then selects the first 4 values to illustrate slicing from the start. It next takes every second value up to a certain point to show how to skip elements, and then uses a step of 3 starting from a later position for more complex stepping. The script also reverses the entire array using a negative step and, finally, selects a group of values near the end with negative indices to show how to access elements from the tail of the array. Each result is printed so you can clearly see how different slice settings change the output. Row and column slices. In 2-dimensional arrays, slicing extends from working with single lists to selecting entire rows or columns using start, stop, and step positions. You can think of the array as a grid where rows run horizontally and columns run vertically. Row slicing lets you choose specific rows, and column slicing lets you choose specific columns. For example, if rows represent patients and columns represent measurements, row slices select certain patients and column slices select certain measurements. you define the slices for rows and columns separately, and the array library combines them to produce the subarray you want. To understand row and column slicing, remember that the first index refers to rows and the second to columns. If you slice by choosing certain rows and leaving columns open, you select specific observations but keep all their features. If you instead slice by choosing certain columns and keeping all rows, you select specific variables such as temperature and humidity for every observation. In both cases, the result is still a two-dimensional array, just with fewer rows, fewer columns, or both, depending on how you slice. Using step values when slicing rows and columns lets you sample data at regular intervals, which is useful for working with large datasets. You can, for example, take every second row to thin out a dense sensor recording while keeping all columns, or select every third column to quickly simplify a spectrum. In image processing, choosing every nth row and column can crop regions or create lower resolution thumbnails. By practicing these slicing techniques, you become more skilled at extracting exactly the subarray you need from a larger dataset. Python code, row and column slices. This section explains how to select specific rows and columns from a two-dimensional NumPy array. It shows how to take slices of rows while either keeping all columns or choosing only certain columns. It also demonstrates how to take slices of columns while either keeping all rows or selecting only certain rows. The goal is to understand how slicing works in both directions, so you can flexibly access parts of a two-dimensional array. We begin by importing the NumPy library, which is a key tool in Python for working with arrays and performing numerical calculations efficiently. This step makes NumPy's array handling and numerical functions available for use. With NumPy imported, the rest of the script can rely on its powerful features for manipulating and processing numerical data. We use a two-dimensional array from NumPy to store temperatures in Fahrenheit. The array has 3 rows and 4 columns. Each row represents a different day, and each column represents an hourly temperature reading. This structure organizes the data by day and time, making it easy to access and work with specific temperature values as needed. We begin by printing the entire data array so we can clearly see its grid-like structure. This reveals how the data is organized, with each row corresponding to a day and each column representing an hourly temperature measurement. Viewing the full array makes the layout and values easy to understand, which is important before performing any slicing or other manipulations on the data. We begin by selecting the first 2 rows of the data array, which correspond to the first 2 days of temperature measurements. This is done by slicing from the start of the array up to, but not including, the 3rd row, while keeping all columns. As a result, we extract the temperature values for every hour across those 2 days. We then print this subset to confirm that it correctly shows the hourly temperatures for the first and second days. We begin by selecting all rows from the data array, but only specific columns. Using a slice with a start of 0, an end of 3, and a step of 2, we pick out the first and third columns while skipping the second. This gives us 2 hourly measurements for every day in the dataset. We then print these selected columns so we can see the temperatures recorded at those particular hours for each day. We extract a specific subset of the data array by taking every second row, which keeps the first and last days while skipping the middle one. At the same time, we select only the last two columns, which correspond to the final two hourly measurements. This slicing focuses the data on particular days and hours of interest. We then print this subset to clearly show the temperatures recorded at those selected times. This script shows how to slice a two-dimensional NumPy array that stores temperature data for 3 days with 4 hourly readings each day. It first prints the full array to reveal its structure, then selects the first 2 rows to display temperatures for the first 2 days across all hours. Next, it slices out the first and third columns for every row to focus on 2 specific hours for all days. Finally, it takes every second row and only the last 2 columns, skipping the middle day and showing temperatures for the last 2 hours on the first and third days. Together, these examples demonstrate how slicing can efficiently extract specific subsets of data by choosing particular rows and columns. Multi-axis slicing. When working with multi-dimensional arrays, slicing lets you select organized blocks of data by choosing a slice along each axis, such as rows and columns. You can think of it like cropping an image, where you decide how much to remove from each side to get a smaller picture. In the same way, multi-axis slicing extracts subarrays while preserving the original layout and the relative positions of elements along every axis. Multi-axis slicing means choosing ranges along each axis of a dataset separately, then combining them. Along the first axis, such as rows or time steps, you pick a start, stop, and optional step, just like slicing a one-dimensional array. You do the same along the second axis, such as columns or variables, which together defines a grid of selected positions. For instance, in a table where rows are patients and columns are medical measurements, you might select patients 10 through 49 and only the blood pressure and heart rate columns. This same idea extends to higher dimensions, such as selecting a block from a 3-dimensional scan or a sequence of frames from a video. Multi-axis slicing lets you sample data at regular steps along each axis so you can reduce data density while keeping a coherent subarray. For example, you might take every second row and third column from a large array to create a lower resolution summary that is faster to analyze. In climate data, this could mean selecting every 5th latitude and 10th longitude to form a coarse grid that still shows large-scale patterns. And in image processing, it can involve taking alternate pixels in both directions to downsample a region. Overall, this approach preserves the original structure but with fewer elements, making analysis more efficient. Python code, multi-axis slicing. This section focuses on demonstrating multi-axis slicing using small NumPy arrays. It explains how to combine row and column slices to select specific rectangular regions within an array. By printing the results of these slices, you can clearly see which subarrays are being selected. The goal is to build intuition for how multi-dimensional slicing works in practice. We begin by importing the NumPy library, which is a key tool in Python for working with arrays and performing fast numerical calculations. This step makes NumPy's efficient array handling and numerical functions available to us. With NumPy imported, we can use its powerful features throughout the script to manage and process numerical data effectively. We begin by using a numerical computing library to create a 3x4 array of numbers from 0 to 11. This sequence is automatically generated and then reshaped into 3 rows and 4 columns. The resulting array represents measurements in inches, arranged like a small table. This tabular structure makes the data easy to see, work with, and modify in later steps. We first print a short message to signal that we are about to show the entire array, which gives context for what follows. Then we display the full set of measurements so listeners can understand how the data is arranged in rows and columns. Seeing the complete layout makes it easier to follow and interpret any slicing or selection operations that come next. In this step, we take a slice of the measurements array to extract a smaller section of the data. Specifically, we select the first 2 rows and columns 1 through 3, forming a rectangular block. This subarray lets us isolate and work with just that portion of the data, which can make further analysis or visualization more focused and manageable. The code first announces that it will show a specific slice of the array, focusing on rows 0 through 1 and columns 1 through 3. It then prints the stored slice so you can see exactly which part of the original array was selected. This lets you visually confirm that the correct rows and columns have been extracted from the data. In this example, we slice an array by taking every second row and every second column within specified ranges. For the rows, we go from 0 to 3, but keep only rows 0 and 2. For the columns, we go from 0 to 4 and keep only columns 0 and 2. The result is a smaller subarray that forms a checkerboard pattern of the original data, showing how step values in slicing let you efficiently sample elements across multiple axes. We first print a short message to explain that we are about to show a slice of the array that takes every second row and every second column. This message clarifies the pattern used to select elements. We then display the variable that stores this stepped slice so we can see exactly which elements were chosen from the original array. Together, the message and the printed slice help us visually confirm that the slicing operation worked as intended. This script shows how to use multi-axis slicing on a 3x4 NumPy array. It first prints the full array to reveal its structure, then slices out a smaller 2x3 section by taking the first 2 rows and selected middle columns. It also demonstrates step slicing by choosing every second row and every second column, producing a 2x2 subarray. Overall, it illustrates how NumPy slicing across multiple dimensions enables flexible selection and manipulation of array data. Views and copies. When slicing returns views. In NumPy, slicing usually creates a view rather than a completely new array, meaning the sliced result shares the same underlying data as the original. A view is simply another way of looking at part of the same data without duplicating the values. When you slice with a start, stop, and step, NumPy builds a new array object that stores only metadata, such as shape and strides, while the actual data remains in place. This design makes it efficient to work with large datasets, because you can operate on portions of the data without copying everything into new memory. You can think of a multidimensional NumPy array as a regular grid of values in memory. When you slice it using simple ranges that follow this structure, NumPy can usually reuse the same underlying data without creating a new array. Common operations like selecting certain rows or taking every second element along an axis then produce a view rather than a copy. Because a view shares the same data, any changes you make through the slice also change the original array. In NumPy, not every slicing operation produces a view. It depends on how regularly the data is accessed in memory. When the result can be described with simple offsets and strides, such as with basic slices, reversing an axis, or taking evenly spaced elements, NumPy usually creates a view for efficiency. In many practical tasks, like working with climate or financial time series data, you can often expect slicing to return a view, meaning changes through the slice also change the original array. Knowing when slicing creates a view helps you manage memory better and avoid unintended modifications to your data. Python code. When slicing returns views. Slicing an array often creates a view that shares the same underlying memory as the original data. This means that when you change values in the slice, those changes appear immediately in the original array. Demonstrating this behavior helps beginners see that slices and their source arrays can be tightly linked. With this understanding, they can better predict when slicing will produce shared views and when it might not. We begin by importing the numerical computing library NumPy, which is essential for working with arrays and performing fast numerical calculations. This step enables us to use its powerful tools for creating, manipulating, and analyzing arrays. With NumPy available, the rest of the script can efficiently handle the numerical operations it needs. We begin by creating a simple one-dimensional array in NumPy with the values 10, 20, 30, 40, 50, and 60. This gives us a clear set of numbers that are easy to work with and observe. Using this basic array, we can then demonstrate how slicing works and how changes made through a slice can affect the original array because they share the same underlying memory. We take a slice of the original array by selecting elements from index 1 up to, but not including, index 3, using start and stop positions. This operation extracts a portion of the array without creating a separate copy. Instead, the slice, called the mid-slice, is a view that shares the same underlying memory as the original array. As a result, any changes made to the mid-slice will also change the corresponding elements in the original array. We begin by printing the original array to show its initial state, which gives us a baseline for comparison. Then we print a middle slice of the array created using simple start and stop positions, so we can see this subset before any changes are made. Later, when we modify the slice and print everything again, we can compare these outputs and clearly observe how changes to the slice also affect the original array because they share the same underlying memory. When we change the second element of the slice called mid-slice to 999, we also change the original array because that slice is a view, not a separate copy. This means the slice and the original array share the same underlying memory. As a result, any modification made through the slice is immediately reflected in the original array. This behavior shows how slicing can create shared views that directly affect the source data. We print the original array after changing the slice to show that modifying the slice also changes the array, proving they share the same underlying memory. Then we print the middle slice itself to clearly show the specific change that was made. Together, these outputs reinforce the idea that the slice and the original array refer to the same data. In this example, we create a slice of an array by taking every second element using a step of 2. The important point is that this slice is a view, not an independent copy. Because it shares the same memory as the original array, any changes made to the slice will also change the original data. This behavior shows how slicing can produce shared views rather than separate arrays. In this example, we change the first element of a slice that selects every second element from the original array. Setting this value to -5 directly modifies the shared memory, so the original array is updated as well. This shows that such slices act as views, meaning any change to the slice is immediately reflected in the original data. The final print statement shows the current contents of the original array to highlight how slice operations affect it. Because slices are views that share the same memory as the original array, any changes made through them are reflected in the original data. By printing the array at the end, we can see the combined result of all these modifications. This confirms that the slices and the original array are linked through shared underlying data. This example shows that when you slice a NumPy array, the slice often shares the same memory as the original data. Starting with a one-dimensional array, taking a slice of the middle part and changing a value in that slice immediately changes the corresponding value in the original array. This means the slice is a view, not an independent copy. Later, taking another slice that skips every other element and modifying it again updates the original array. Together, these actions demonstrate that NumPy slices commonly operate on the same underlying memory, which makes data manipulation more efficient. Detecting copies with base. When working with NumPy arrays, it is important to know whether two arrays share the same underlying data or are independent copies. The base attribute helps with this by showing whether an array is a view linked to another array or owns its data. If the base attribute is not null, the array is a view that depends on another array's data. If the base attribute is null, the array is the original source and stores its data independently. When working with array slices or similar operations, it is important to know whether you are dealing with a view or a copy. You can check this by looking at the base attribute to see if the subset is linked to the original data. If the base points to the original array, any changes you make to the subset will also change the original. If the base is null, the subset is independent, so modifying it will not affect the original dataset. This simple check helps you predict the impact of your operations before you proceed. In practical NumPy workflows, the base attribute is a helpful way to check whether arrays share memory or are independent copies. For example, when you slice a large image into tiles and then transpose or reshape them, you can inspect the base attribute at each step to see if the new arrays still refer back to the original image. This matters for large datasets, such as satellite images or medical scans, where unnecessary copies can waste memory and slow processing. By regularly checking the base attribute, you learn which operations create views and which create copies, allowing you to manage memory more efficiently and safely. Python code: detecting copies with base. Demonstrate how the base attribute in NumPy distinguishes between views and independent copies of an array. Start by creating an original array, then form a slice that acts as a view and also create an explicit copy for comparison. By printing the base attribute for each, you can see that the view reports the original array as its base, while the independent copy has no base. Finally, modify the data through the view to show that changes affect the original array, confirming that they share the same underlying data, unlike the separate copy. In this lesson, we use the NumPy library, a key tool for numerical computing in Python that supports efficient array operations and mathematical functions. NumPy is especially useful for working with large datasets and performing complex calculations quickly. In our script, we rely on NumPy to create arrays and then use the base attribute to show how to tell whether an array is just a view of existing data or an independent copy. This helps you understand how data is shared or duplicated in memory when working with NumPy arrays. We begin by using a numerical computing library to create an array containing the values 10, 20, 30, 40, 50, and 60. This array is stored for later use, and we immediately display its contents so we can clearly see the original values. Establishing this initial array and viewing it is important because it provides a reference point for comparing any views or copies we create from it later on. We first take a slice of the original array from index 1 to 4, which creates a view that still shares its data with the original array. Then we make a separate copy of that same slice, which does not share data with the original. This setup lets us compare how a shared view and an independent copy behave differently when the data is changed. We first display the values accessed through the slice view to show which elements of the original array it is referencing. Then we display the values in the copy to show the elements that were explicitly duplicated from the original array. This comparison highlights that the slice view still depends on the original data, while the copy holds its own independent set of values. To check whether an array slice is a view or a copy, we look at its base attribute. If the slice's base points to the original array, it is a view and shares the same underlying data. If we then examine another array created as a copy and see that its base attribute is set to none, this tells us it is a completely independent array that does not share data with the original. We change the first element of the slice view to 999, which directly updates the slice because it shares the same underlying data as the original array. After printing the slice, we see the new value, confirming the modification. When we then print the original array, we observe that its corresponding element has also changed, demonstrating that altering a slice view automatically alters the original array it is based on. This explanation shows how the base attribute in NumPy distinguishes between views and independent copies of an array. An original array is created. Then a slice is taken as a view, and a separate explicit copy of that slice is made. The slice view reports the original array as its base, meaning they share the same underlying data, while the copy has no base, meaning it is independent. When the slice view is modified, the original array changes as well. But the copy does not, clearly demonstrating the difference between shared data in a view and independent data in a copy. Preventing unwanted changes. When you slice an array, you often get a view that shares the same underlying data, so changing the view also changes the original array. You can think of a view as just a different perspective on the same values. This means you must be deliberate about when you want edits to affect all shared data and when you want to keep data separate. For example, if you slice out a region's temperatures from a climate dataset and do a unit conversion, first decide whether that change should update the main dataset. If you want to preserve the original data for later analyses, create an independent copy before making modifications. When working with data slices that you plan to modify, assume they are risky unless you know they are independent copies. A safe habit is to create a separate copy before doing in-place operations, such as scaling or filling in missing values, especially when moving between stages of a workflow. In a machine learning pipeline, this means selecting the features you need, then making a working array to change while keeping the original data untouched. This approach protects your baseline data so you can always return to a clean reference version later. Preventing unwanted changes in your data is not just about making backups, but about designing your transformations with clear intent. Make it obvious which arrays or datasets are the main sources and which are temporary by using clear names and avoiding long chains of in-place modifications. Structure your work so each step either reads from shared data without changing it or operates on clearly marked copies. For example, in financial analysis, a team can safely experiment with fraud detection on copies, while the official records remain untouched. This approach protects data integrity and supports trust in your results. Python code, preventing unwanted changes. This section explains that when you slice an array, the slice may be a view that still shares data with the original array, so changing the slice can accidentally change the original. It then shows that creating a copy of the slice instead breaks this link, so modifications affect only the new array. Finally, it compares the behavior of a view slice and an independent copy slice to highlight how shared data works and why using a copy can prevent unwanted side effects. In this lesson, we use the NumPy library, a key tool in Python for fast numerical work with arrays and mathematical functions. We apply NumPy to create and manipulate arrays that represent temperature data. This lets us investigate how operations like slicing and copying work, and how they can affect the integrity of the underlying data. We begin by using a numerical computing library to create an array that stores Fahrenheit temperatures for 4 nearby cities. The array is filled with the values 70, 72, 68, and 75 degrees. These values act as sample real-world temperature data. This array will then be used for further manipulation and analysis in the code. We take a slice of the original Fahrenheit temperature array that contains only the middle two cities. This slice is a view, which means it shares the same underlying data as the original array rather than making a copy. Because they point to the same memory, any change made to the slice will automatically update the corresponding values in the original array. In this example, we directly modify a view slice by adding 10 to each of its elements, similar to adjusting or correcting sensor readings. Because the view shares the same underlying data as the original array, any change made to the view is immediately reflected in the original. This shows that altering a view can unintentionally change the original data. It is important to remember this link whenever you work with views. This part of the code shows that when you modify a view slice, you also change the original array. Because the view shares the same underlying data, any updates made through the view are reflected in the original temperatures. After making these changes, the code prints a message to indicate that the original temperatures have been altered, and then prints the original array so you can see the actual updates. We reset the temperatures back to their original Fahrenheit values, so we can clearly compare what happens when we change a view slice versus a copy slice. By reinitializing the array, we remove any previous modifications. This gives us a clean starting point and lets us observe the behavior of the code in a controlled and consistent way. We create a slice of the Fahrenheit temperatures for the middle two cities, but we use the copy method, so it becomes a completely separate array. This new array does not share data with the original one. As a result, any changes we make to the copied slice do not affect the original temperatures. This allows us to experiment safely without causing unintended side effects in the original data. In this step, we adjust the elements of the copied slice by adding 10 to each value, similar to correcting sensor readings. Because this slice is an independent copy of the original array, any modifications we make here stay local to the copy. As a result, the original data remains unchanged and unaffected by these updates. We print a message to emphasize that after changing the copy of the slice, the original temperature data does not change. This shows that working with a copy protects the original array from unintended modifications. By printing the original Fahrenheit temperatures, we confirm they are unchanged, reinforcing the idea that using a copy instead of a view keeps the source data safe. This script shows the difference between working with a view and a copy of a NumPy array. It starts with an array of Fahrenheit temperatures, then takes a slice without copying it. Because this slice is just a view that shares the same memory, increasing some of its values also changes the original array. When the script instead creates a copy of that slice, the copied data is stored separately. Increasing the values in the copy no longer affects the original temperatures, demonstrating how copying prevents unintended changes to the original array. Reshape and flatten views. Automatic dimension inference. When you reshape an array in NumPy, you are reinterpreting the same block of memory with a new arrangement of rows, columns, or dimensions. Automatic dimension inference lets you leave one dimension unspecified and NumPy computes it from the total number of elements. This is useful when you know how many values you have but want a flexible shape, such as for image batches or time series. In many cases, this reshaping produces a new view of the data rather than a full copy. As long as the new shape is compatible with how the data is stored in memory. Automatic dimension inference in NumPy relies on the fact that the total number of elements in an array stays the same when it is reshaped. If you leave one dimension unspecified, NumPy computes its size by dividing the total number of elements by the product of the dimensions you did specify. For example, if you choose a window length for sensor readings, NumPy can determine how many complete windows fit into the data. This only works when the division gives a whole number. Otherwise, the reshape fails so that no data is lost or duplicated. Automatic dimension inference in NumPy makes reshaping easier by letting NumPy compute one missing dimension, but it does not change whether the result is a view or a copy. That still depends on how the original data is laid out in memory and whether the new shape is compatible with that layout. When the data is stored contiguously, reshaping often produces a view. If the array has been sliced or transposed so that contiguity is broken, NumPy may need to create a copy instead. In short, inference only fills in one axis size and does not relax the underlying memory layout constraints. Python code, automatic dimension inference. This section explains how to use the reshape function in NumPy with a -1 as a placeholder so that NumPy automatically infers the missing dimension size. It compares the results of manually specifying all reshape dimensions with the automatically inferred size to show they produce the same overall shape. It also points out when the reshaped array is just a new view that shares the same underlying memory as the original data, rather than creating a full copy. We begin by using the NumPy library in Python, which is designed for efficient numerical computing with large, multi-dimensional arrays and matrices. NumPy includes many mathematical tools that operate directly on these arrays. In this script, it is specifically used to show how to reshape arrays and how NumPy can automatically infer one of the dimensions, so we do not have to specify every size when changing an array's shape. We begin by using a numerical computing library to create a one-dimensional array with 12 elements, containing the numbers from 0 through 11. We then display the shape of this array, which confirms it has a single dimension with 12 entries, and we print the array itself. This simple setup prepares us to explore how the same data can be reshaped into different forms later on. We take a one-dimensional array and reshape it into a two-dimensional array with 3 rows and 4 columns using the reshape method from NumPy. This operation simply reorganizes the 12 elements into the new layout without changing the data. After reshaping, we check the new shape and the values to confirm that the transformation worked as intended. This approach is straightforward, but requires knowing the exact dimensions we want in advance. We use the reshape function for NumPy to change an array so it has 4 columns, and we let NumPy figure out how many rows are needed by passing -1 as a placeholder. This tells NumPy to automatically compute the correct number of rows, while keeping the total number of elements the same. After reshaping, we print the new shape and the data to confirm that the transformation worked as intended. We use the reshape function from NumPy to change the array so it has 3 rows, while letting NumPy automatically figure out how many columns are needed. To do this, we specify 3 as the number of rows and use -1 for the columns, which tells NumPy to infer that value from the total number of elements. In this example, NumPy determines that the reshaped array should have 3 rows and 4 columns. We then print out both the new shape and the contents of this reshaped array. When we reshape an array, the new view can share the same memory as the original data. If we then change the first element of this reshaped array, for example, setting it to 99, the first element of the original array also becomes 99. This behavior shows that both arrays are not independent copies, but different views of the same underlying memory buffer. Understanding this helps explain why changes in one view can directly affect the other. This material explains how the reshape function in NumPy can automatically infer one dimension when you use a -1 as a placeholder. Starting from a one-dimensional array with 12 elements, it is first reshaped manually into 3 rows and 4 columns. Then the same shape is obtained by letting NumPy infer either the number of rows or the number of columns using the -1 placeholder. The key idea is that these reshaped arrays share the same underlying memory as the original array. So changing an element in the reshaped version also changes that element in the original. Ravel versus flatten. To convert a multidimensional array into one dimension, you can use either the ravel function or the flatten function. Both give you a one-dimensional result, but ravel only changes the view of the original data and does not create a new copy. In contrast, flatten always creates a new independent array. This distinction matters when you plan to modify the data or work with large datasets, because creating unnecessary copies can waste time and memory. When you use the ravel operation on an array, it usually creates a view of the original data, so any changes you make to the raveled version also change the original array. This can be efficient for global edits, such as adjusting the brightness of an image, but it requires care to avoid accidental modifications. In contrast, the flatten operation always creates a new, independent copy of the data. Changes to this flattened copy do not affect the original array, which makes it safer when experimenting or when you need to preserve the original values. When choosing between ravel and flatten, focus on efficiency, safety, and clarity. Ravel is better for performance-critical work on large arrays because it avoids extra memory use and lets you modify the original data in place. Flatten is better when you need a completely separate copy, such as when passing data to external libraries or machine learning tools, so that changes do not affect the original array. By deciding whether you need a shared view or an independent copy, you can keep your code both efficient and predictable. Python code, ravel versus flatten. This section explains the difference between ravel and flatten when turning an array into one dimension. You should demonstrate that ravel returns a view that shares data with the original array, so changing values in the raveled version also changes the original. In contrast, flatten returns a copy of the data, so modifying the flattened array does not affect the original values. The goal is to clearly show how shared data versus copied data leads to different behavior when you make changes. In this lesson, we begin by using the NumPy library, a key tool in Python for efficient numerical computing. NumPy lets us work with arrays and many mathematical functions, which makes it well-suited for handling numerical data. In our script, we rely on NumPy to create and manipulate arrays so we can examine how the ravel method and the flatten method behave differently. We begin by creating a simple two-dimensional array in NumPy, made up of small integers arranged as rows and columns. Each row is represented as a list, and together these lists form the full array. This basic structure serves as a small dataset that we can modify and use to observe how different NumPy methods change the array and its contents. In this example, we first create a raveled view of the original array using a NumPy method that produces a one-dimensional view sharing the same memory. So any changes to this view also change the original array. We then create a flattened version using another NumPy method that returns a new array, which is an independent copy of the data. Because this flattened array does not share memory with the original, modifying it does not affect the original array. The key idea is that ravel gives a view, while flatten gives a separate copy. We begin by printing the original array before making any changes, so we have a clear baseline for comparison. Seeing its initial state makes it easier to understand how each method we apply later alters the array. This first display is essential for recognizing the effects of the subsequent operations and for tracking how the data evolves step by step. When we change the first element of the raveled view of an array, such as setting it to 99, we are directly modifying the original array because the raveled view shares the same underlying memory. This means any edits made through the raveled view are immediately reflected in the source array. This behavior contrasts with a flattened copy, where changes affect only the copy and leave the original array unchanged. The key idea is that a raveled view is linked to the original data, while a flattened version is independent. We first print a message to signal that we are about to show the state of the original array after changing its raveled view. This prepares us to observe how modifying the raveled view affects the original data. We then display the current contents of the array so we can clearly see the impact of the change made through the raveled view, which shares the same underlying memory as the original array. When we change the second element of the flattened copy and set it to 77, the original array stays the same. This happens because the flattened version is an independent copy, not just another view of the original data. As a result, any modifications made to the flattened copy do not affect the source array. This behavior shows that using the flatten operation creates a separate array that can be safely changed without altering the original. The code prints a message to show that the flattened version of the array has been changed, then displays the contents of this modified flattened copy. This behavior illustrates that the flattened array is an independent copy, not just a different view of the original. As a result, any changes made to the flattened copy do not affect the original array, because they do not share the same memory. This explanation compares the ravel and flatten methods in a numerical computing library using a simple 2x2 array. When you use ravel, it creates a view that shares memory with the original array. So changing an element in the raveled version also changes that element in the original. In contrast, flatten creates a completely separate copy of the data. So modifying the flattened array does not affect the original. The key idea is that ravel returns a view that can alter the original data, while flatten returns an independent copy. C and F order. When reshaping and flattening arrays, it is important to understand memory order. In C or row major order, the last axis changes fastest, so elements next to each other in the last dimension are stored together. In Fortran or column major order, the first axis changes fastest, so elements in the first dimension are stored contiguously. NumPy supports both layouts, and your choice determines whether a reshape can reuse the existing memory as a simple view or must allocate new memory. This decision can significantly affect performance, especially for large datasets. Think of a sales spreadsheet with days as rows and products as columns. In C order, the data for each day across all products is stored together. So if you flatten the array, you move through products one day at a time. In Fortran order, the data for each product across all days is stored together. So flattening moves through days one product at a time. When you reshape an array in NumPy, it keeps whichever order is already used in memory. And if the new shape is compatible, the reshaped array can be a view that reuses the same underlying data without copying it. When you transpose an array in NumPy, it usually creates a view that changes how the data is stepped through in memory, which may not match standard C or Fortran order. If you then reshape this transposed array as if it were in C order, NumPy may need to allocate new memory, turning the view into a copy. However, if the new shape is compatible with the current stride pattern, the array can stay a view and avoid extra memory use. This understanding of memory order and reshaping is especially important for large datasets, such as those in climate models or medical imaging, where unnecessary copies can be costly. Python code, C and F order. Explain how reshaping arrays works differently in C order and Fortran order, focusing on how elements are laid out in memory. Show that changing the flattening order changes the one-dimensional sequence of elements you get from the same data. Also, emphasize which reshaping operations produce new views that share the original memory, and which ones instead create independent copies of the data. We begin by using the NumPy library, a key tool in Python for numerical work with arrays and matrices. NumPy lets us store data efficiently and apply many mathematical operations to these structures. In this script, we use NumPy to create arrays, reshape them into different dimensions, and flatten them back into one dimension. We also observe how these reshaping and flattening operations relate to the way the data is stored in memory. We begin by using a numerical computing library to generate the numbers from 1 to 6 and arrange them into a two-dimensional array. This array is reshaped into 2 rows and 3 columns, forming a simple dataset that could represent something like days and products. We then display this original array so we can clearly see its 2-row, 3-column structure. We begin by flattening the two-dimensional array using C order, which is a row major layout, where elements are taken row by row and the last axis changes fastest. To do this, we use the ravel function from the numerical library to convert the array into a one-dimensional sequence. After flattening, we print this sequence to observe how the elements are arranged under this row major ordering. We flatten the two-dimensional array using Fortran order, which means we move through the data column by column rather than row by row. In this column major approach, the first axis changes the fastest as we traverse the array. After flattening, we print the resulting one-dimensional sequence to observe how the elements are arranged under this ordering. We reshape a 2x3 array into a 3x2 array using C order, which stores data in row major form. This reshaped array is only a view of the original, meaning they share the same underlying memory rather than creating a separate copy. When we change the first element of the reshaped view to 100, that change is immediately reflected in the original array. Printing the original array then reveals the modification, showing that reshaping with C order can directly affect the original data. We reshape a 2x3 array into a 3x2 array using Fortran order, which fills the new array column by column instead of row by row. Then we change the first element of this reshaped array to 200. Because the reshaped array is only a view of the original, this change also updates the original array. Finally, we print the original array to confirm that modifying the view directly affects the underlying data. This script shows how reshaping and flattening a two-dimensional array works in C and Fortran memory orders. It starts with a 2x3 array and flattens it so that C order lists elements row by row, while Fortran order lists them column by column. The array is then reshaped into a 3x2 form using both orders. When an element is changed in the reshaped array created with C order, the original array also changes, proving they share the same memory. The same effect occurs when reshaping with Fortran order, confirming that both approaches create views that are linked to the original data. In this lecture, you learned to use basic slicing and step slicing to select subarrays from one-dimensional and multidimensional ndarrays. Distinguish between views and copies in NumPy 2.2.6 and predict when slicing operations share memory. And reshape and flatten arrays while reasoning about when the resulting arrays are views of the original data. In the next lecture, Lecture B, we will go over advanced indexing.
Thank you for your attention. See you all in the next lecture.